From where we were last time, digital signatures. I may have finished this slide. I remember talking about the URL at the bottom, electronic signature. Basically, the idea is that the signature should be easy to produce and easy to verify and very difficult to forge. That's the summary. So we are looking for a function which is easy to do but very easy to difficult to reverse, but at the same time it will be easy to verify, right? So it's like just like the public key stuff where it's very easy to encrypt as well as decrypt, but very difficult to break the key, right? So it's very difficult to forge. So now we are going to talk about I think 3 different schemes for digital signatures. And all of them basically what they do is they simply have some function which if you compare, if they are 2 are equal, then basically you got the signatures validated. So the first one is by Elgamal, and it uses exponentiation just like before we saw in Diffie-Hellman and Elgamal algorithm that we talked about earlier. And so obviously exponentiation means discrete logarithm is difficult, while you can easily exponentiate something, but you cannot take the anti-log, you cannot do the log. So you take a large prime Q and you take a private key XA and you make a public key A raised to XA, where A is the root, primitive root of Q. So this is, everybody knows A raised to XA, they don't know XA. Now you take a hash of the message using some hash function, and the hash to be between 0 and Q minus 1. Because if it is Q, that is same as 0, right? So 0 and Q minus 1. Choose the random integer K, and this is what we call the message key. So now there are several keys here. One is the user key, which was XA, and then we have a message key, so which is chosen just for this message, and then for the next message you will use another key. So K is the message key, and just like K is a private key, you have A raised to K, which is a public message key in that sense, right? So you have S1 is A raised to K mod Q. So you have a message, you have a key which is kind of a public key, and now you calculate K inverse basically in this Q minus 1, right? So K inverse, you do that same tabular method. You can write K and Q minus 1 and then somehow find K inverse. Once you have found that, then you find S2, which is M minus XA S1. So you can compute all of this because you know XA. Other people cannot compute this. So anyway, so you know S1, which is this public key, and then M, which is the hash, and K inverse that you computed from your random number K. So S2 is what you send out. So mod Q minus 1 is what you send out. S2 is 0, then you start with a new K, because that is easy to break. So you just get until S2 is non-zero, and so you send S1 and S2. All right. Again, one more time. S1 is like a public key for the message. S2 is this expression. Now, any user can verify that this is a valid signature by doing this. They can calculate V1, which is A raised to M mod Q, because they can calculate the hash. The message is in clear, and if it is not in clear, you will have another encryption key and you will have it clear. Anyway, you have the M they can calculate, so they can calculate A raised to M mod Q. They can calculate V2, which is your public key, YA, raised to S1, this number, and S1 raised to S2 mod Q. If V1 is equal to V2, then this signature is valid. Why? Because YA is alpha raised to XA, or A raised to XA, raised to S1, and S1 is A raised to K, and then raised to S2, right? So when you put all this together, it becomes A raised to XA S1 plus K times S2, XA S1 plus S2 is this much, which is K inverse. So K inverse and K cancel out, and you get M minus XA S1. XA S1 cancel out, and only thing you get is A raised to M, which is V1. So that's how you do the Elgamal digital signature. Basically, you have per message key, you get the message kind of public key, and then you calculate this S2 based upon the hash and your own private key, and then you send S1 and S2 out. Everybody can see S1 and S2. Everybody can verify that this signature is valid. Okay? Any questions about that?
This is not a small K. This is the same as a capital K, right? S2 is 0, start with a new capital K.
So there is no small k anywhere in this slide. I'm sorry. This is somewhat little bit confusing. Sometimes they use little k, sometimes they use big K. I remember seeing a small k somewhere before, but not here, okay? So on this slide, there is no little k. Okay? If you want, I mean, you could just use little k everywhere, and I would do that, because see, if I were to write a book, which I have done many, I would keep consistently the uppercase and the lowercase. What does the uppercase mean? What does lowercase mean? What does little k mean? What does big K mean? There is no meaning here at all. They just randomly, wherever they find the algorithm, they copy the notation without changing it, without making any form. So that's why it's confusing, right? So it's all capital K here. And why it is capital? It's just behind me. I just don't want to change myself, because you are going to read the book and then you'll have to do the correlation. So I just left it as it is. Yeah.
There's a small K, but start with K.
Okay, so that should be capital K. Okay, so let us change that to capital K, 13-9. Good. Anything else? All right. So there is an example here. So we are going to use with 19. Of course, it won't be 19 in the real world. But just for example, let's say the 19 is a prime number, and we know all its primitive roots. We did it in one of the chapters before. All the primitive roots of 19. 10 is one of them. So we select 10, and you randomly select any XA, which happens to be 16 here. So YA is 10 raised to 16 mod 19, and you know how to calculate all these things, so I won't go back again. And so you get 4. Now hash comes out m equal to 14 already given. The hash is 3, 4. Sorry, hash with hash m equal to 14 as, no, sorry. Okay, no, hold on. So hash is 14. So what we do is we choose k equal to 5, which was just another random number, because 18 and 5 is 1, q minus 1, and k should be relatively prime. So here it cannot be, basically 5 has to be such that it is relatively prime, right? So it cannot be 9, 3 or anything like that, or 2, 3 and 9. So anyway, so we have 5. Now S1 is equal to 10 raised to 5, which is 3. And K inverse is 11. And then S2 is 11 times 14 minus 16 times 3. Now, so this is little m minus S1, no, minus S1 times 16, which is YA, right? So, XA, hold on, XA and YA. backspace. Ya is a raised to something and xa is a number. And you use xa here. Right? So here we are using xa. xa is 16. Right? xa is 16. That gives you 4. So that's how it results as 3, 4. S1, S2. Now, any user can verify the signature by computing V1. V1 is a raised to m mod q. M is 14 mod 19, and you can calculate that to be 16. Then V2 is ya raised to S1 and S1 raised to S2. So ya is 4. Where is ya? Ya is right here, 4. 4 raised to S1, 3 times 3 raised to 4, S1 raised to S2. That gives you 16. 16 is equal to 16, digital signature is valid. Okay? There is another scheme by Schnorr, and this also uses very similar things. It uses exponentiation in the finite Galois field, exactly like Diffie-Hellman. And so the main differentiator here is that most of the work you can do before you need it. When you get the message, there is small work, not too much work. Okay, so you use a prime modulus P. Now let's see. A minute ago we had a prime modulus Q. Now here we have P. Okay, so modulus P, and P minus 1 has a prime factor Q. Now Q has become a factor. Okay, so the thing is they don't, I mean, basically this is why it causes confusion. Now Q is a factor and P is a modulus. Previously Q was the modulus. So anyway, for every algorithm you have to remember what the notation is. I may advise the author to probably take care of this kind of issues in his books. Because anyway, so P minus 1, Q is a factor. And typically P is 1024 bit, Q is 160 bit, which is the hash size. So you choose P and Q and choose A such that A raised to Q is 1 mod P. Alright, so this requires quite a bit of work. So what has happened is that a lot of people, I mean, not everybody does not do this, because some people have done this work and they have A, P, and Q, which everybody can use. So that's the advantage, is that you don't have to go out and look for P and Q and then find a prime factor Q and then find A raised to Q equal to 1. So actually A, P, and Q are global parameters for all, in the sense that everybody knows those numbers. You can go to some RFCs. I actually did go to one point to the RFCs, and they list A, P, and Q. Alright, and those A, P, and Q will have this property which is shown here. Q will be a factor of P minus 1, and A raised to Q will be equal to 1 mod P. That part is clear so far? Alright, with those global parameters, then when you get a message, all you have to do is, well, not even a message right now, you just select your private key, S. Actually, your private key is minus S probably. And then you compute a public key, V equal to A raised to minus S mod Q. So this is not a straight exponentiation. After exponentiation, there is an inversion. A raised to minus S mod Q. Actually, it could have been simplified, because for every prime Q, A raised to something minus 1, either Q minus 1 or Q is 1. right? If q is a prime for every number a, that is 1, and so this could be q minus s or q minus s minus 1. One of these is just positive number. But anyway, so we start with a negative number a raised to minus s mod q, and we get a v, little v. When you get the message, then you generate another random number r, and you compute a raised to r mod p. Hold on, maybe I was wrong here. Q is prime, yeah, and p is prime. Both of them are prime. Okay, so that's good. So a raised to r mod p. Now you got x. So what you do then is you put x at the end of the message. So this double line, you know what that means? That means concatenation. So you take these bits and put these bits at the end. So these, for example, we said the x would be 160 bits we said, right? So these will be an additional 160 bits in addition to the message. And now you hash this thing. You hash the whole message, and hash comes out to be E. Then you compute R plus SE. R is this number. S is the number that you selected before. And E is computed here. So R plus SE mod Q, and then you send out E comma Y, where Y is this R plus SE. And you send out this hash. Okay? And the way you verify is that you compute x prime is equal to a raised to y. Y is given, so you can, and a is well known, is a global constant. A, p, and q are global constant. So everybody knows a raised to y, and then v raised to e. Now, how do you get v? V is here, a raised to minus s mod q. So v is the public key, which is basically known for you. I mean, everybody knows your public key, so that's why they know a raised to minus s. So v raised to e is given here, and you do mod p, and then if this comes out, and then you take m concatenated with this number, and you do the hash, you get an E, then you're all set. So basically this, you should be able to get back X, A raised to R mod P from Y. That's all you do. So this is X computed. A raised to Y, B raised to E. Y is given, B is your public key, E is given. So you can compute that. And then if X prime is equal to X, then the signature is valid. So we come from Elgamal to Schnorr, because with Schnorr, the idea is that you do very little work after you get the message. And that is the only work you do. When you get the message, you have already computed everything. You have computed basically, what you do is you choose a random number R, compute X, and then compute E. For every message, you need a new number R, and then you can compute E. So then came about digital signature standard, again by NIST, and published as a 5th standard, Federal Information Processing Standard. It has been revised many times, uses SHA hash algorithm. So now you know what is SHA. And you might see the word DSS. DSS is the standard and DSA is the algorithm. Digital signature algorithm, digital signature standard. And the second version of same FIPS 186, 2000 includes RSA, elliptic curve, etc. for hashing. Anyway, DSA for signature only, right? Digital signature only. So this is for signatures. And the way it works is that you create a 320-bit signature with 512 to 1024-bit security is smaller and faster than RSA. So I'm going to describe actually this in more detail. So this is not the only slide. Actually, the next 2-3 slides are on DSA. And security depends upon difficulty of computing the discrete logarithm. So this is all same thing. And it is also another variant of Elgamal and Schnorr. So everything is very similar to what we have said so far. So again, you have a global public key values P, Q, and G. Now the symbols have changed. Previously we had A, Q, and P. Right? Those are the same variables, but then their symbols now are P, Q, and G. Okay? Because maybe the standard uses P, Q, and G, maybe Schnorr used that number, and maybe Elgamal used that, so just keep using the same variables. And so P, Q, G are basically where Q is a 160-bit prime number, P is a very large prime, larger than L minus 1 and less than L, so it is basically a L bit long, where L is 512 to 1024 bit and is a multiple of 64. Okay. So let me explain this. L is the length of the prime number. So the length of the prime number is multiple of 64, not the prime number itself, right? Prime number obviously is not a multiple of anything, but it cannot, and originally they said that you should either use 64-bit or 128-bit or something like that, multiple of 64, and the suggested values of 512 to 1024. Now, they have done two things. Actually, this multiple thing has been taken off, which is not listed on the slide, but it is in the book. So it doesn't have to be multiple of 64. And second thing is, the length is not limited to 1024 either. Now you can have signatures which have length of 3000 bits. Alright, Q is 160-bit prime divisor of P minus 1, like before. The roles have changed, isn't it? Previously, yeah, P was the prime number, okay. Alright, now you calculate G, which is H raised to P minus 1 divided by Q. H is a number such that H raised to P minus 1 divided by Q is more than 1, is not 1. So basically G should not be 1. So you select a H so that G is more than 1. Now interesting thing is, generally H equal to 2 is used. So that's very easy. If you put H is equal to 2 raised to big prime divided by Q, 2 raised to that is very easy because all you do is 1 bit and then all zeros. Right? So H equal to 2 makes the life easier because G is very easy to compute. So now you have P, Q, and G. Alright, and these are all global. So here's the thing, I mean, since these are all global, you don't have to worry about it. You will just read it from a book and use it. Now when you get a message, then, now here it says you choose a random private key. So you're not going to choose a private key every day or every hour. Generally, you will see in the next few chapters, you will get a private key like we set from certificate, and you will have a public key which you will put it on a website and people can read it anytime they want. So that is a permanent thing, right? So choose a random private key means, in this algorithm it says that, but now the world works by certificates where it is all permanent private key. So you have a private key Q, X, and then you calculate your public key G raised to X mod P. Okay. G raised to X mod P. To sign the message, you select a random message key, K, and it should be basically for each message you get a random K, and then you calculate that z raised to k mod p mod q. All right. If r is 0, then you choose another k. So basically, you just select k so that it is r is non-zero. And then you use this formula, hm hash of the message plus. So this is not concatenation, this is an addition. xr, multiplication of r and x, your private key, multiplied by k inverse mod q, you get s. If you get s equal to 0, you go back to the beginning. Select another k, select another r, select another, find another s. And then you send r and s. Now, I tried to show this in this diagram. This is a variant of what is in the book. Basically, what this says is that m is the message. You give it to the hash function and you get h of m, that number. You also feed to this box x and q, which are the numbers you have selected. Q is a global number, x is the number you have selected. And from here, we get r and k. R and k. So how do you get r? You feed k, and then you get g raised to k mod q mod p mod q, and you feed p, q, and g here. So you get an r, feed that r here, and you get an s. And this s is lowercase. I think this looks like uppercase to me, but I will change it to lowercase. Anyway, so that s is, you send r comma s, r and s. This is your signature. All right, how do you verify it? To verify, you compute V and R. R is already sent to you. R was sent to you like this. R and S were sent to you. So you compute V. How do you compute V? Compute W is equal to S inverse mod Q. S is sent to you, so you can compute S inverse mod Q. And then U1 is hash of M multiplied by W mod Q. And then U2 is R times W. R was given to you directly anyway. So R times W mod Q. And then you calculate V equal to G raised to U1, Y raised to U2 mod P, mod Q, whole thing mod Q. If you get V equal to R, then signature is valid. So why is this analysis valid? Is because, let's just do the math. I mean, you can do the math. G raised to U1, and just forget, if you forget all the mods, it's very easy to verify. But G raised to U1 is G raised to RW. Y raised to G raised to U1 is G raised to little mw. Capital H, capital M is little m. So little mw, G raised to little mw, and Y is G raised to X. So you have G raised to X raised to RW. So now you have G raised to MW plus G raised to XRW. I forgot the letter, but XRW, I think. So MW plus MRW, and that is equal to V. And the V is sorry, R equal to V. V was that, and R equal to, R is simply G raised to K. So if you do all that math, you should come out with G raised to K. And I will leave that you to verify that that is the correct thing. If you don't, then we can work on it. basically, just like we did in the other two signatures. If you put everything here together, it should come out that V is equal to simply G raised to K. Now there is a slight confusion to me. So there is a little bit more than this, because this picture which came from the book actually uses the S prime and M prime, and so there is a little bit more than in verifying all this. It says G raised to U1, it says G raised to H M prime. And U1 is only G raised to HM. So what is M prime? Oh, it's a -1? I can't read it? Oh my God, my English. Is it really -1?
Yeah. Same as the
Okay, anyway, so here's the thing. I mean, this is one of the things that you should do anyway, just to understand this thing, to verify that B equal to R means signature is valid, right? And you can do that because we did it for the other two algorithms. Okay? All right. And this picture simply says the same thing all over again. How do you produce, and how do you, so basically, okay. So now you could use this. So this is the DSS signature and this is the RSS signature. This is not the same thing, I'm sorry. RSS signature basically would mean that you take the message and you hash it and then you encrypt it using a private key and you concatenate it. So you just send the message and the encryption of the hash. At the other end, with the public key, you can get out and you get the hash. So that's a straightforward. This is the RSA approach. With the DSS approach, you have all these numbers, public G, private A, okay. I'm just going to leave it alone. Actually, the thing is, let's see, what is private and what is public here? Private is X. Where is A? So I don't know, what is A? But anyway, so private, there is a X private key, private number, and then the K is the per message number, and then you get this signature, you send it over, you send that S and R, and then somehow you do the calculation and they should compare. V should be equal to R. Okay? So those are the 4 signature schemes we saw actually. We saw the RSS signature schemes, we saw Al-Gamal, we saw SNAR, and we saw DSS. And the idea is that, the common idea is that, not in RSA, but most of the, now in the schemes that we talked about, you have a per message key, you have your own private key, you use the per message key first, get the hash they don't specify, you can just use the hash, SHA-1, get the hash, and then do some calculations, and then at the other end you can do correspondingly the other calculation to verify that this is valid. Okay, so 3 things. Digital signature depends upon the message and some information unique to the signer to prevent forgery. That information is the private key. That information is the private key of the signer, and actually the random number K that was selected, prevent forgery and denial. Any word should be able to verify it. Al-Gamal, SNAR, and DSS signature use per message secret key, and they are based upon exponentiation. Actually, everything is based upon exponentiation. Even RSA is based upon exponentiation. DSA produces a 320-bit signature. So what are the 320-bit? Well, your signature is R and S. Each of them is 160-bit long. So that is your 320-bit. Okay. Okay. Homework 13. If you get s equal to 0, a new value of k should be generated. The question is why. So you should just go back and see what happens if you have s equal to 0. Then what becomes very easy. Suppose Alice signed a message M using DSA with a specific value of k, and then the k value was compromised. So somebody found out k. Can Alice use her private key for future digital signatures? Now k was the message key. And so the question is, if somebody knows your message key, can they calculate your private key? Your private key was XA, remember? That's different than K. But can they calculate K easier? Show that the private key can be computed in both cases. Okay, so somehow in both cases you have to show that if S equal to 0, XA can be easily calculated. DSA has XA, right? X, it has X. X. That's your private key. So X can be easily calculated in both of these cases. All right, any questions?